A faint smudge of light hides our universe's strangest secrets. That is the Triangulum Galaxy, the third largest spiral in our local cosmic neighborhood. It looks peaceful from 2.8 million light-years away, but we are about to journey directly into its heart. You will discover 25 of the most bizarre objects ever found, from a shockingly quiet supermassive black hole to stellar explosions that defy all logic. What could cause a star to race across the galaxy at unimaginable speed? And why is there a mysterious structure there that resembles a perfect red geometric shape? By the end, you will see our cosmic backyard in a completely new and thrilling light. Are you ready to question everything you thought you knew about the nature of galaxies? Our journey begins at the very heart of the galaxy, where a profound silence reigns. In most large galaxies, the core is a raging, brilliant furnace powered by a supermassive black hole, a cosmic monster that devours matter and blasts out energy. But the center of the Triangulum Galaxy tells a different story. Here, astronomers have found a supermassive black hole that is not just quiet, it is almost eerily dormant. This is our first strange object, the Triangulum supermassive black hole anomaly. While the black hole at the center of our own Milky Way, Sagittarius a star, has a mass of about 4 million suns, and Andromeda's core beast weighs in at a staggering 100 million solar masses, the central black hole in M33 is a lightweight. Current estimates place it at only around 1.5 thousand to 5,000 solar masses. That is not a typo. It is thousands of times less massive than its counterparts. This presents a monumental puzzle. Why is the engine at the center of this grand spiral galaxy so comparatively tiny and dim? You would expect a galaxy of this size, with its beautiful, well-defined arms, to host a much more formidable gravitational anchor. Its faintness suggests it is consuming very little material, meaning its accretion disk, the swirling ring of superheated gas that normally shines with intense X-rays, is either absent or incredibly faint. One leading theory is that the Triangulum Galaxy has simply had a very peaceful history, without major galactic mergers or close encounters funneling vast amounts of gas and stars toward its center. The black hole has been on a cosmic diet, starved of the fuel it needs to grow and become active. Another, more intriguing idea is that this black hole might represent a different path of galactic evolution altogether, perhaps forming from the direct collapse of a giant gas cloud in the early universe, bypassing the typical growth stages. Imagine looking at two powerful engines, one roaring with fire and the other sitting cold and still. That is the visual contrast when you simulate the bright, energetic disks of Andromeda and the Milky Way against the dark, quiet pit at the heart of Triangulum. Its silence is not an absence but a question. What does this tell us about how galaxies and their central black holes co-evolve? The answer might rewrite our understanding of what it means to be the heart of a spiral. But the quiet at the galaxy's core is more than made up for by a spectacular explosion of light and life elsewhere. Just off-center, a stellar factory of unimaginable scale churns out new suns. This is our second strange object, the giant star-forming region known as NGC 604. To call it a nebula feels like an understatement. It is a cosmic metropolis of birth, a vast cloud of glowing hydrogen gas stretched across nearly 1,500 light-years. If you could place it inside our own Milky Way, it would outshine even the famous Orion Nebula, swallowing it whole with room to spare. Within this colossal pink and red cloud, the process of star creation has been dialed up to an extreme. NGC 604 is not just forming stars, it is specializing in the most massive, hottest, and shortest-lived varieties imaginable. Astronomers have identified over 200 young, brilliant stars within it, and many of these are true behemoths, some weighing more than 60 times the mass of our own Sun. These are the rock stars of the stellar world. burning their nuclear fuel at a frantic pace and destined to explode as supernova in just a few million years. Their fierce ultraviolet radiation ionizes the surrounding hydrogen gas, causing the entire nebula to glow with an ethereal pink light, while their powerful stellar winds act like cosmic blowtorches. These winds carve out immense cavities and sculpt the gas into delicate, bubble-like structures that stretch for hundreds of light years. You can see these bubbles in detailed telescope images, looking like fragile soap bubbles blown by giants, each one marking the violent outflow from a cluster of newborn stars. What makes NGC 604 truly exceptional, even for a galaxy as active as Triangulum, is its sheer intensity. The rate of star formation happening here is staggering, a concentrated burst of cosmic construction on a scale rarely witnessed so close to home. It represents a peak of galactic activity, a place where the fundamental forces of gravity, radiation, and stellar winds are playing out on a grand, almost theatrical stage. This single region is a powerful reminder that a galaxy's story is not told by its quiet center alone, but by these brilliant, chaotic nurseries where the next generation of stars and perhaps planets is being forged in fire and light. The brilliant stellar nursery NGC 604 shows us the raw power of creation, but elsewhere in Triangulum, a different kind of power is at work, one that devours light itself. Our third strange object is not a glowing cloud, but a pinpoint of invisible, searing energy known as M33X7. It is classified as an ultraluminous X-ray source, a mouthful that describes one of the most extreme phenomena in modern astronomy. Imagine an object no larger than a city, yet shining with the X-ray brightness of 10 million suns. That is the scale of power we are talking about. This source, detected by space-based X-ray telescopes like Chandra and XMM Newton, outshines every other point of X-ray light in the entire Triangulum Galaxy. It is so luminous that for decades, astronomers could not explain how such a small object could produce so much energy. The leading theory points to a stellar mass black hole, the remnant of a collapsed giant star, but one that is behaving in a way that defies all expectations. Normally, a black hole of this size has a theoretical limit to how brightly it can shine, a rule based on its mass and the physics of its accretion disk. M33X7 smashes right through that limit, so what is fueling this cosmic overachiever? One possibility is that we are seeing a trick of geometry. Perhaps the black hole's accretion disk and the jets of material it spits out are funneled or beamed directly toward our line of sight. Like a lighthouse beam aimed perfectly at Earth, this beaming effect could make the source appear far brighter than it truly is from other angles. Another, more thrilling idea is that this is not a stellar black hole at all, but a rare intermediate mass black hole, a missing link between the small ones from dead stars and the supermassive giants at galactic centers. An object with hundreds or thousands of solar masses could easily account for the ferocious X-ray output. Then there is the nature of the feast itself. The black hole might be stripping material from a companion star at such an insane, unsustainable rate that the infalling gas piles up in a denser, hotter disk than physics should allow, creating a supercritical state that unleashes this torrent of radiation. Visualize this for a moment. In an optical image of Triangulum, you see a serene tapestry of stars and nebulae. Then you overlay the X-ray data, and a single, brilliant white dot flares to life in a seemingly ordinary region of the spiral arm. That dot is M33X7, a raging pinpoint of power hidden within the calm stellar landscape. It represents a fundamental puzzle in high-energy astrophysics, a laboratory for testing the absolute limits of how matter behaves under the most extreme gravity imaginable. Is it a cosmic illusion, a hidden monster, or a system breaking its own rules? The answer continues to pull us deeper into Triangulum's mysteries. While M33X7 rages with invisible fury, another region of the galaxy glows with a quiet, almost artificial geometry. Our fourth strange object is a nebula that looks like it was drawn with a ruler. Deep within Triangulum's spiral arms lies a peculiar structure often called the Red Rectangle Nebula Analog, named for its stunning resemblance to a famous and mysterious object within our own Milky Way. At first glance, it defies the typical cosmic aesthetic of billowing clouds and chaotic filaments. Instead, this nebula presents a stark, angular shape, with a distinct rectangular or even X-like form, framed by what appear to be straight, intersecting lines of luminous gas. This is not the work of alien architects, but the breathtaking signature of a star's final act. The bizarre shape is the direct result of bipolar outflows. Imagine a dying star, a red giant in its last throes, not expelling its outer layers in a uniform sphere, but firing them out in two powerful, opposing jets along a single axis. These jets, composed of gas and dust, slam into slower-moving material ejected earlier in the star's life. The collision sculpts the material into those distinct conical shapes, and from our vantage point, looking nearly edge-on at this double cone structure, we see the unmistakable outline of a rectangle or an X. The color adds another layer of mystery. The deep red hue which gives the object its name does not come from the familiar glow of hydrogen. Instead, it is emitted by a very special kind of dust. This nebula is rich in complex carbon-based molecules, essentially soot created in the atmosphere of the dying star. When illuminated by the star's hidden ultraviolet light, these carbon-rich dust grains fluoresce with that characteristic brick red color, a telltale sign of a particular type of stellar death that seeds the galaxy with the building blocks of future planets and potentially life. Finding such a precise and rare object in another galaxy is like discovering a familiar, intricate fossil on a distant continent. It tells us that the fundamental physics of stellar death, the processes that forge heavy elements and sculpt beautiful nebulae, are universal laws. By studying this red rectangle analog in Triangulum, astronomers gain a priceless external perspective. They can observe this type of system in a different galactic environment, free from the foreground clutter of our own Milky Way, to check if the rules we've deduced at home truly hold everywhere. This geometric ghost is a cosmic confirmation, a signpost that even in death, stars follow a profound and beautiful order. That precise geometric nebula shows a star dying by the rules, but elsewhere in Triangulum, a star is breaking them with sheer velocity. Our fifth strange object is a candidate runaway hypervelocity star, a sun moving so fast it could one day escape the galaxy's gravitational grasp entirely. While we have found these cosmic speedsters in our own Milky Way, spotting a strong candidate in another galaxy like Triangulum is a different kind of breakthrough. This star is not just drifting with the galactic rotation, it is tearing across the spiral arm, its motion a stark outlier against the orderly flow of its stellar neighbors. The forces required to achieve such speed are almost unimaginable. The leading theory points to a violent cosmic slingshot. Imagine a binary star system, two stars locked in a mutual dance. If one of them goes supernova, the catastrophic and asymmetrical explosion can act like a natural rocket engine, kicking the surviving companion star with such force that it is ejected at tremendous speed. Another possibility involves a close gravitational encounter with the supermassive black hole at a galaxy's center, though Triangulum's quiet core makes this less likely here. The star's trajectory tells a story of immense past violence. By measuring its radial velocity, how fast it moves toward or away from us, and its proper motion across the sky, astronomers can trace its path backward. This reverse engineering often points to a birthplace in a dense star cluster or a region of recent supernova activity, the scene of the crime from which it was launched. Finding such an object in Triangulum is invaluable because it gives us a clean, external laboratory. In our own galaxy, mapping the precise origin of a runaway star is incredibly difficult, like trying to trace a single bullet's path in a crowded battlefield after the fact. But in Triangulum, with its face-on orientation, we get a clearer, less cluttered view of the stellar population and dynamics. We can potentially identify the cluster it fled from and even estimate when the cataclysmic kick occurred. Visualize this for a moment, a single point of light on a chart of the galaxy, not following a gentle curve with the spiral arm, but cutting across it like a scratch on a photograph. Its path is a straight line vector of pure momentum, a testament to a moment of apocalyptic energy that forever changed its destiny. This runaway candidate is more than a fast star. It is a tracer bullet, illuminating the hidden forces of gravitational interaction and stellar death that continually reshape galaxies from within. It proves that even in the vast, seemingly serene disk of a spiral galaxy, individual stars can live stories of incredible drama and escape. That runaway star is a solitary survivor of a stellar catastrophe, but sometimes the aftermath of such a catastrophe leaves a ghostly monument for all to see. Our sixth and seventh strange objects are a pair of supernova remnants, the expanding clouds of debris from exploded stars, but these are not simple, round bubbles. Their twisted forms tell a specific and violent story. The first remnant possesses a shell that is wildly asymmetric. Instead of a smooth, spherical husk expanding evenly into space, this one looks lopsided, almost shredded. One side of the shell may appear bright and well-defined, while the opposite side is faint, fragmented, or even missing entirely. This bizarre morphology is a direct fossil record of the explosion itself. It suggests the supernova was fundamentally uneven. Perhaps the dying star had a severely lopsided structure, with denser material on one side inhibiting the blast wave, or maybe the explosion mechanism, the collapse of its iron core, was intrinsically turbulent and off-center. Imagine setting off a firecracker inside a ball of clay that has one thick wall and one thin wall. The resulting debris cloud would not be round, it would be distorted, with shrapnel flying farther in one direction. That is the kind of chaotic death this remnant preserves. The environment into which it exploded also plays a role. If the star died in a region of space where the interstellar medium was patchy, with dense clouds on one side and empty voids on the other, the expanding shockwave would encounter more resistance in some directions, slowing down and brightening as it plows into the denser gas, while racing ahead unimpeded into the emptiness elsewhere. This remnant is not just a cloud of gas, it is a forensic snapshot of the final milliseconds of a star's life and the crowded neighborhood where it met its end. The second remnant presents a different kind of interaction, one that is actively creating cosmic particle accelerators. This supernova shell is not expanding into a uniform void, but is slamming directly into a massive, pre-existing cloud of cold interstellar gas and dust. The collision is spectacular in its violence. The multimillion-mile-per-hour shockwave from the supernova plows into this dense, slow-moving wall of material, compressing it, heating it to extreme temperatures, and causing it to glow intensely across multiple wavelengths. You can often see this as a bright, sharp arc of emission, a bow shock where the two forces meet, but the real magic happens at that collision front. The tremendous energy of the impact does not just produce light, it acts as a natural particle accelerator, far more powerful than anything we could build on Earth. Charged particles like protons and electrons become trapped between the magnetic fields of the shockwave and the cloud, bouncing back and forth and gaining incredible speed until they are hurled into space as cosmic rays. These are the same high-energy particles that constantly rain down on our own planet. By studying this remnant in Triangulum, astronomers can observe this acceleration process in action, seeing how a stellar explosion can energize the very fabric of the galaxy. The remnant's shape becomes molded by the cloud, flattening on one side as it pushes against this immovable obstacle, while perhaps billowing out freely in other directions. Together, these two remnants are masterclasses in celestial storytelling. One reveals the internal violence of the star's death throes, while the other showcases the dramatic external dialogue between a cataclysm and its environment. They prove that in the Triangulum Galaxy, even the ghosts of dead stars carry unique and revealing shapes. The ghostly remnants of supernova map violent ends, but another kind of star in Triangulum pulses with a steady, living rhythm that astronomers depend on. These are Cepheid variable stars, the universe's most reliable mile markers. Their brilliance waxes and wanes in a perfectly predictable cycle, and the period of that pulsation is directly tied to their true, intrinsic brightness. By measuring how bright they appear from Earth and comparing it to how bright they truly are, we can calculate their distance with remarkable precision. It is this celestial yardstick that helped Edwin Hubble prove other galaxies existed beyond our own. Yet within Triangulum, astronomers have found a Cepheid that marches slightly out of step. This anomalous variable star is our eighth strange object, a cosmic lighthouse whose signal is just a little bit off. Its pulsation period and its observed brightness do not align as neatly as our well-established models predict. It might be slightly too bright for its period or perhaps too dim. This small discrepancy is a big deal because the entire cosmic distance ladder, our method for measuring the scale of the universe, is built upon the trusted consistency of these stars. So what could cause a Cepheid to break the rules? One strong possibility lies in the star's composition. Cepheids are not all made of the same stuff. A star's metallicity, the amount of elements heavier than hydrogen and helium within it, can affect its internal structure and how it pulsates. Triangulum is known to have a lower overall metallicity than our own Milky Way. This particular Cepheid might simply be a product of its environment, a star with less metal in its veins that behaves differently than the solar neighborhood Cepheids we use to calibrate the rulebook. Another fascinating twist could be that this Cepheid is not dancing alone. It might be part of a binary system with an unseen companion star. The light we measure from it would then be a blend of two stars, not one, throwing off our careful calculations of its true luminosity. The gravitational tug of a partner could even subtly influence its pulsation rhythm. Then there is the most profound possibility of all, that our understanding of the physics inside these aging, unstable giant stars is still incomplete. The relationship between period and luminosity might have a subtle dependence on factors we are only beginning to map. Finding this anomaly in Triangulum is a gift because it allows us to test and refine our models in a new galactic laboratory. If our best cosmic yardstick has a slight wobble, we need to find it and correct for it. Otherwise, every measurement of distance beyond it carries that tiny error forward, potentially skewing our perception of the universe's expansion and age. This one quietly pulsing star, therefore, is not just a local curiosity. It is a sentinel guarding the accuracy of our map of the entire cosmos. The steady pulse of a Cepheid variable gives us cosmic measurements, but another star in Triangulum might be hiding a monstrous secret within its heart. Our ninth strange object is a candidate for one of the most bizarre theoretical constructs in all of astrophysics, a Thorne-Zitkow object. Picture, if you will, a star that should not exist. It begins with a dance of doom, a close binary system where one star is a massive red giant, and the other is a tiny, ultra-dense neutron star, the collapsed core of a supernova. Over time, the bloated outer atmosphere of the giant star engulfs its neutron star companion. Instead of an immediate cataclysm, the neutron star spirals inward, sinking through the tenuous outer layers and finally coming to rest at the very center of the giant. There, it becomes a new kind of engine, a neutron star core inside a red giant envelope. This is not a collision but a merger, creating a stellar chimera. For a time, this hybrid star would shine in the sky looking like a normal, though perhaps unusually cool red supergiant. Its true nature would be betrayed only by the chemistry happening deep within. The searing temperatures and intense densities at the interface between the neutron star's surface and the surrounding hydrogen-rich gas would trigger a unique form of nuclear cooking known as the slow neutron capture process. This exotic fusion pathway produces very specific heavy elements in unusual abundances, elements like lithium, rubidium, molybdenum, and others that are normally scarce in the atmospheres of old giant stars. In Triangulum, astronomers have identified a red supergiant star whose light, when broken into a spectrum, shows precisely these strange chemical fingerprints. Its atmosphere appears polluted with an excess of these rare elements, a signature that matches the theoretical predictions for a Thorne-Zitkow object. The neutron star at its core would act like a cosmic alchemist, forging strange atomic nuclei in the turbulent maelstrom where its incredible gravity meets the star's inner furnace. Confirming this candidate would be a discovery of the first order. It would validate a decades-old theoretical prediction about stellar evolution and demonstrate an entirely new way for stars to exist and produce heavy elements. These objects are thought to be incredibly rare and short-lived, perhaps lasting only a few 100,000 years before the neutron star's accretion of material causes it to either collapse into a black hole or trigger a spectacular outburst. Finding one would give us a front-row seat to a previously unseen phase of stellar life, a hidden factory for rare materials. It would be like discovering a mythical creature, long spoken of in equations, finally made flesh and blood in the cosmos. This strange star in Triangulum, with its peculiar chemical makeup, is a tantalizing hint that the universe is still capable of assembling structures more wondrous and improbable than we have yet dared to dream. That theoretical stellar chimera forges rare elements in a hidden furnace, but elsewhere in Triangulum, a cloud of potential lies utterly dormant. Our 10th strange object is a dark globule, a dense, cold knot of gas and dust drifting through a spiral arm like a cosmic ink blot. Known more formally as a Bok globule, these are often the cradles of future solar systems, the very sites where gravity begins its slow work of pulling matter together to ignite new stars. Yet this particular cloud is a study in stillness. It is a pocket of profound quiet, a nursery that refuses to birth anything at all. The darkness of this globule is not an illusion, it is a statement. The dust within it is so thick and cold that it completely blocks the light from any stars behind it, creating a stark, black silhouette against the glowing backdrop of the galaxy. Inside, temperatures hover just a few degrees above absolute zero, and the gas is so dense that molecules can barely move. This is precisely the environment where we expect star formation to begin, but here the process has stalled. Why would a cloud with all the raw materials remain so stubbornly inert? The answer often lies in a delicate balance of forces. For a cloud to collapse and form a star, the inward pull of its own gravity must overcome the outward pressure of the gas and any internal turbulence or magnetic fields that support it. This particular globule might be in a state of perfect, fragile equilibrium. It could be just too warm, or its internal magnetic fields might be acting like a rigid skeleton, holding the cloud up against its own weight. Perhaps it simply lacks a trigger. In more active stellar nurseries, the shock wave from a nearby supernova or the intense radiation pressure from massive young stars can slam into a stable cloud, compressing it and tipping the scales in gravity's favor. This dark globule might be floating in a relatively peaceful part of the galaxy, isolated from such cosmic violence. There is also the possibility that we are catching it in a fleeting moment of cosmic time. It could be in an extremely early pre-stellar phase where the collapse is just beginning, too subtle for our current instruments to detect. The first faint whispers of a future star might be happening inside, a slow, gravitational sigh that will take hundreds of thousands of years to become a roar. Studying such a quiescent cloud is in many ways just as important as studying the brilliant fireworks of a place like NGC 604. It helps astronomers define the precise thresholds of star birth. By measuring its mass, density, temperature, and magnetic field, we can understand the exact conditions that must be met for a cloud to fail, to remain forever a potential that was never realized. This dark blot against the starry canvas is a control experiment written across the galaxy, a reminder that the universe is filled with both furious creation and profound, pregnant silence. That profound silence within the dark globule is a prelude on a cosmic scale, but the story of Triangulum extends far beyond the bright disk we can easily see. Our 11th strange object is not a single point of light or a cloud, but the galaxy's own ghost, a vast, extended halo of ancient stars. This faint, spherical shroud envelops the entire spiral structure, stretching hundreds of thousands of light years into the empty intergalactic void. For a long time, astronomers assumed Triangulum's halo would be relatively modest, a thin and wispy relic of its formation. Recent deep observations, however, have revealed something startling. This halo is far more massive and richly structured than any model predicted. It contains a significant population of old, metal-poor stars, ancient suns that formed when the universe was young, and they are arranged in streams and clumps, not a smooth distribution. This complexity is a direct challenge to our understanding of how this galaxy was built. A quiet, isolated spiral should have a calm and simple halo, the leftover debris from its initial collapse billions of years ago. The intricate patterns we see tell a different tale, a history of violence and interaction. The most compelling suspect in this cosmic mystery is the Andromeda Galaxy, the giant next door. Andromeda's immense gravitational pull is a dominant force in our local group. The structures in Triangulum's halo look like the scars from a close encounter, perhaps a grazing past that happened billions of years in the past. During such a flyby, Andromeda's gravity would have violently stirred Triangulum's outer stars, pulling them out into long, looping tidal streams that have only slowly settled into the clumps we detect today. It is a fossil record of a past assault preserved in the motions of countless ancient suns. This forces a dramatic rethink of Triangulum's life story. It may not be the isolated, peaceful spiral we once thought. Instead, it could be a survivor of a gravitational battering, its outer layers stripped and reshaped by a titan. The sheer mass of the halo also suggests Triangulum is more substantial than it appears, its true gravitational weight hidden in this dim, sprawling cloak of stars. This changes the entire dynamic of the local group. The future merger between Andromeda and our own Milky Way will not be a simple duel. Triangulum, with its substantial halo and unexpected history, could play a more active role, perhaps being drawn into the collision earlier or influencing the final structure of the new galaxy that forms. So when you look at an image of the Triangulum Galaxy, remember you are only seeing its brilliant heart. Its true form is that of a giant, cloaked in the faint, structured ghost light of its ancient and turbulent past. That ghostly halo tells a story of past collisions, and you can see a direct echo of that violence written in the galaxy's very bones. One of Triangulum's graceful spiral arms carries a distinct warp, a region where the perfect symmetry of the pinwheel breaks down. This asymmetric arm is our 12th strange object, a glaring imperfection in an otherwise orderly structure. When you look at a high-quality image of M33, you immediately notice the difference. Most of its arms flow in smooth, logarithmic curves from the core, lined with bright blue star clusters and pink nebulae, but one arm, often the northern arm, appears noticeably brighter, more kinked, or even slightly detached in places. It looks like a river of stars that has burst its banks, spilling its luminous contents into a broader, more chaotic swath. This is not a random flaw, it is a signature. Spiral arms are not fixed structures like the spokes of a wheel. They are density waves, moving patterns of compression that travel through the galactic disk like ripples on a pond. Stars and gas move into these waves, get squeezed, and trigger star formation, creating the bright lanes we see. Normally, these waves maintain a beautiful symmetry. An asymmetry this pronounced points to a major gravitational disturbance. The prime suspect, once again, is a past encounter with Andromeda. A close gravitational tug from a massive neighbor can violently perturb the orderly rotation of a galaxy's disk. It can stir up the gas, enhance the density wave in one specific region, and even trigger a burst of star formation that makes that arm blaze with newborn stars. Think of it like dragging a stick through a smooth, rotating whirlpool of cream and coffee. The pattern would instantly distort, with one spiral ridge becoming higher, brighter, and more turbulent than the others. That is likely what we are witnessing. Another possibility is that this arm is still feeling the effects of a smaller, digested satellite galaxy. Triangulum may have cannibalized a dwarf companion in the distant past. As that smaller galaxy was torn apart, its stars and gas would have been strewn along an orbital path, superimposing a stream of material onto one of Triangulum's native arms, thickening it and lighting it up with the collision-induced birth of stars. This creates a hybrid structure, part original spiral arm, part galactic wreckage. The consequences are profound. This distorted arm is not just a cosmetic feature. It represents a region of heightened astrophysical activity. The enhanced density means more cloud collisions, more gravitational collapse, and ultimately, more stellar nurseries like the colossal NGC 604. It is a stellar factory operating at overdrive because of ancient violence. This single kinked arm, therefore, is a living timeline. Its brightness tells us about a past event. Its shape reveals the direction and strength of the gravitational pull that caused it, and the stars being born within it are quite literally made from the aftermath. The asymmetry is a wound that has healed into a scar of brilliant light, a permanent mark on the galaxy's face that reveals its dramatic history to anyone who knows how to look. Deep within the dusty lanes of that warped spiral arm, a different kind of glow emerges, one invisible to the human eye. Our 13th strange object is an unidentified infrared source with a peculiar chemical fingerprint. It appears in telescope surveys not as a point of visible light, but as a bright, warm beacon in the infrared spectrum, and its light carries the clear spectral signature of silicate dust. This is the telltale mark of sand, of tiny, glass-like grains floating in space. Finding such a signature is common, but pinpointing its exact origin becomes a fascinating cosmic detective story. Astronomers must work through a process of elimination, weighing the evidence against known celestial blueprints. The first and most likely suspect is a dust-enshrouded star. Imagine an aging giant star, like the one that may have created the red rectangle nebula, but in an earlier phase. It could be pumping out vast amounts of gas and dust, creating a thick, opaque cocoon around itself. The star's visible light is trapped and absorbed by this shroud, heating the dust to a few hundred degrees. That warm dust then re-radiates the energy as the infrared glow we detect, and the silicates within it imprint their signature on the light. Another strong candidate is a protoplanetary disk, a vast, swirling pancake of gas and dust surrounding a newborn star. Within this disk, microscopic silicate grains are the fundamental building blocks of rocky planets. As these grains collide and stick together, eventually forming pebbles, then planetesimals, and finally worlds, they are warmed by the young star's light and emit that characteristic infrared signal. In our own solar system, we are essentially living inside the debris of such a disk that glowed billions of years ago. Yet sometimes, the evidence does not neatly fit either of these familiar templates. The source might be too bright, too variable, or located in an unusual environment. Could it be something more exotic? Perhaps it is the aftermath of a colossal collision between two rocky bodies in a distant solar system. a catastrophic event that vaporized crusts and mantles, creating a temporary, intense cloud of silicate vapor that is now cooling and condensing back into dust. Or maybe it is a previously unknown phase of stellar evolution, where dust production reaches an extreme level. The stubbornness of some unidentified infrared sources lies in this ambiguity. Without additional clues like detection in X-rays, which would point to an accreting black hole or neutron star, or specific gas emission lines that reveal stellar winds, the object remains a silhouette. It is a warm, dusty something, its true nature hidden behind a veil of its own making. This particular source in Triangulum is a reminder that for all our advanced telescopes, the universe still holds points of light that refuse to be categorized. They sit in our catalogs not as answers but as persistent questions, challenging us to look deeper, to develop new instruments, and to imagine possibilities beyond our current celestial library. While dusty infrared sources hide their nature, the motion of stars can reveal a hidden predator. Our 14th strange object is a candidate intermediate mass black hole, suspected to be lurking at the heart of a dense star cluster in Triangulum. This is the search for a cosmic missing link. We know of small black holes, the remnants of giant stars weighing up to maybe 100 times our Sun. And we know of the supermassive monsters at galactic centers with millions or billions of solar masses. But what about the ones in between? Where are the black holes with hundreds, thousands, or tens of thousands of solar masses? Theory suggests they should exist, possibly as the seeds from which supermassive black holes grow, or as the result of countless mergers in crowded stellar environments. Yet finding definitive proof has been one of astronomy's great challenges. In Triangulum, astronomers turned their gaze to a particular globular cluster, a spherical swarm of hundreds of thousands of ancient stars bound together by gravity. By meticulously tracking the motions of individual stars near the cluster's core, they noticed something unsettling. These stars were whizzing around far too quickly. Their velocities, mapped over time, implied they were orbiting something incredibly massive and completely dark, an unseen gravitational anchor. The math pointed to an invisible object with a mass likely in the range of several thousand suns, far too heavy to be any collection of dim stars or stellar remnants we could not see. The only plausible explanation fitting the data is an intermediate mass black hole. Picture the scene. From a distance, the cluster is a serene, fuzzy ball of ancient light. But zoom into its heart, and the stellar motions paint a picture of chaos, of stars slingshotting around a central point of pure nothingness with terrifying speed. It is as if you observed a swarm of bees circling an empty spot in the air with frantic, organized energy, a clear sign that something invisible and powerful commands their dance. Confirming this candidate would be a monumental discovery. It would provide a crucial piece in the evolutionary puzzle of black holes. Did this object form directly from the collapse of a gigantic cloud of primordial gas in the early universe? Or is it the grim trophy of a globular cluster's violent history, built up over billions of years as stellar mass black holes and neutron stars collided and merged in the cluster's dense core? This potential intermediate mass black hole in Triangulum offers a relatively nearby laboratory to study these questions. Its existence would also help explain how the supermassive black holes in galaxies like Andromeda got their start, perhaps growing from these mid-sized seeds through eons of accretion and merger. A single dark point of gravity, inferred only from the frantic orbits of stars, could therefore unlock chapters in the story of how the most extreme objects in the cosmos are born and grow. The frantic orbits of stars point to a hidden predator, but some stars broadcast their instability for the entire cosmos to see. Our 15th strange object is a luminous blue variable star caught in the act of a spectacular eruption. These are not ordinary stars, they are cosmic powder kegs, some of the most massive and volatile suns in existence. A typical luminous blue variable can weigh 100 times more than our Sun and shine with the fury of millions of them. They live fast and die young, burning through their nuclear fuel in just a few million years, and their entire lives are marked by violent instability. In Triangulum, astronomers have monitored one of these giants as it entered a major outburst. Over a period of months, its brightness skyrocketed, increasing by a factor of 10 or even 100. This was not a slow pulsation like a Cepheid variable, but a catastrophic surface event, a stellar temper tantrum of epic proportions. The cause lies in the star's desperate struggle against its own gravity. At these immense masses, the outward radiation pressure from the core is so intense that it nearly overcomes the inward pull of gravity. The star's outer layers become bloated and loosely bound, like a vast, seething ocean held together by a weak surface tension. Eventually, the radiation pressure wins a local battle. A huge section of the star's outer envelope, often containing more mass than several Earths, becomes unstable and is blasted off into space. This is not a gentle solar wind, but a titanic eruption that can eject a significant fraction of the star's own mass. The ejected material expands outward at thousands of miles per second, forming a dense, opaque shell around the star. As this shell expands and cools, it temporarily hides the brilliant blue surface, making the star appear cooler and redder. Then, as the shell thins and becomes more transparent, the fierce blue light of the stellar core blazes through once more, and the star seems to brighten dramatically. This cycle of eruption, shrouding, and re-emergence is what creates the wild swings in brightness. Each eruption is a cosmic forging event. The material blown off in these outbursts is not just hydrogen and helium. It is enriched with heavier elements fused deep in the star's interior, like carbon, nitrogen, and oxygen. The eruption scatters these newly forged elements into the surrounding interstellar medium, seeding future generations of stars and planets with the chemical diversity needed for complexity and potentially life. An luminous blue variable in outburst is a star literally throwing its own processed guts across the galaxy. These violent episodes are also a prelude to an even grander finale. An luminous blue variable is a prime candidate for a core collapse supernova, and some astronomers believe the most extreme supernova explosions, the hypernova associated with gamma-ray bursts, may come from stars like this. Each major eruption brings the star closer to its ultimate demise, stripping away its outer layers until the unstable core is exposed and ready to collapse. Witnessing one in Triangulum gives us a front-row seat to this rare and violent phase of stellar evolution, watching a star tear itself apart piece by piece before its final cataclysmic detonation. The explosive tantrums of a luminous blue variable reshape entire regions, but the final breaths of smaller stars can be just as artistically complex. Our 16th and 17th strange objects are a pair of planetary nebulae, the glowing funeral shrouds of sun-like stars, but these are not the simple, round bubbles often depicted in textbooks. They are cosmic sculptures twisted into extreme shapes that defy easy explanation. The first nebula displays a dramatic jet-like structure. Instead of a symmetrical shell, it features one or two narrow, collimated beams of gas shooting out from the central star in opposite directions like a precise cosmic blowtorch. These jets, traveling at hundreds of thousands of miles per hour, punch through the slower-moving material the star ejected earlier, creating bow shocks and intricate knots. The second nebula pushes asymmetry even further, presenting a highly bipolar or even quadrupolar shape. A bipolar nebula looks like an hourglass or a butterfly, with two distinct lobes of gas expanding along a single axis. A quadrupolar form is rarer and more startling, appearing as if the star ejected material along two perpendicular axes, creating a structure that resembles a four-leaf clover or a complex X. These bizarre geometries are not random. They are a direct fossil record of the star's death throes, a snapshot of how it shed its outer layers, For a star to produce such focused outflows, the process cannot be a gentle, even puff. Something must be channeling the material, focusing it into tight beams or specific directions. The leading suspect is a powerful magnetic field. As the dying star convulses, its magnetic field, woven through its outer layers, can act like an invisible cage, funneling the escaping gas toward the magnetic poles and launching it into space as those spectacular jets. Another compelling actor is an unseen binary companion. If the dying star has a partner, the gravitational pull of that second star can disrupt the normally spherical mass loss, pulling and squeezing the outflow into an hourglass shape confined to the orbital plane. In extreme cases, the complex gravitational dance of a close binary system could even explain a quadrupolar structure, with outflows directed by the changing tidal forces as the stars orbit one another. Visualize the scene. A star, much like our Sun will be in 5 billion years, reaches its end. It swells into a red giant and begins to gently pulse its outer layers away. But then a hidden process takes over. Perhaps its internal dynamo strengthens, or a nearby companion star stirs the pot. The gentle breeze becomes a structured hurricane, sculpting the expanding gas into a form of stunning precision. These nebulae are more than beautiful. They are diagnostics. By studying their shapes, astronomers can infer the strength of magnetic fields they can never directly measure, and deduce the presence of binary companions they might not even see. Each bizarre form is a chapter in a hidden stellar biography, revealing that even a quiet star's final act can be a display of astonishingly ordered violence. That artistic violence of stellar death enriches the galaxy with new material, but Triangulum is also receiving a massive delivery of pristine fuel from deep space. Our 18th strange object is a high-velocity cloud, a colossal river of cold, neutral hydrogen gas caught in the act of falling onto the galactic disk. This is not a cloud born within Triangulum, but an ancient relic from the intergalactic void, now being captured by the galaxy's immense gravity. Picture it as a cosmic waterfall, a dark stream of primordial matter hundreds of thousands of light-years long, silently cascading down onto the spiral arms. These clouds are fossils from the era of galaxy formation, pockets of gas that never fully collapsed into stars, or they are tidal debris ripped from smaller satellite galaxies during past encounters. Their high velocity in relation to Triangulum's rotation is the key clue to their extragalactic origin. They are moving on a radically different trajectory than the galaxy's native gas. As this immense cloud plows into the outer reaches of the galactic disk, the process is both violent and generative. The leading edge of the cloud collides with the thin, hot gas of Triangulum's halo and disk. This collision creates a shock front, a zone of immense pressure and turbulence that compresses the incoming hydrogen. That compression is the first step toward star birth. It triggers the cloud to fragment into denser clumps and knots, each one a potential future stellar nursery. In a visual simulation, you would see the galaxy from the side, its flat disk glowing softly. From above, a faint, diffuse filament of dark gas streaks in, striking the disk's outer edge. At the point of impact, a ripple of bright blue star clusters ignites, marking where the fresh fuel has sparked a new wave of creation. This accretion is the galaxy's way of breathing in. For Triangulum, it represents a vital infusion of raw material. Stars are constantly forming, living, and dying, locking away heavy elements in stellar remnants and planetary systems. Over billions of years, a galaxy can use up its available gas. A high-velocity cloud is a delivery of hydrogen that has never been cycled through a star, pure, unprocessed fuel that will eventually form new metal-poor stars, perhaps even new planetary systems with a very different chemical history than our own. It is a direct link to the cosmos's raw, primordial state, a river of possibility flowing from the empty darkness into the heart of light and structure. This silent, ongoing rain is how galaxies grow and renew themselves from the outside, a slow-motion feast that will shape Triangulum's future for eons to come. This silent rain of primordial gas feeds the galaxy's future, but Triangulum also broadcasts sharp, enigmatic signals on a completely different wavelength. Our 19th strange object is an anomalous radio source, a point of intense energy that screams across the radio spectrum while remaining utterly invisible everywhere else. Telescopes scanning the sky in optical light see nothing at that location, no star, no galaxy, not even a faint smudge. Infrared sensors find no warm dust, and X-ray observatories detect no high-energy fury. Yet when radio dishes tune in, a bright, persistent signal emerges from that exact spot of empty darkness. It is a shout in a void, a source of power that reveals itself through only one narrow window into the universe. This makes it a profound mystery, a cosmic object that seems to break the rules of how celestial bodies emit energy. So what could possibly produce such a focused, powerful radio signature while hiding every other aspect of its identity? Astronomers have a short list of compelling, yet puzzling, suspects. The first is a distant galaxy, but not a typical one. It could be a radio galaxy, an active galactic nucleus whose supermassive black hole is launching colossal jets of plasma at near light speed. These jets interact with magnetic fields, emitting synchrotron radiation that floods the radio band. If this galaxy is extremely far away, its visible starlight could be redshifted into near invisibility or simply too faint to detect, while its enormous structure-spanning jets still pump out detectable radio waves. Another possibility is a rare type of pulsar, the spinning, magnetized core of a dead star. Most pulsars flash across multiple wavelengths, but some, especially older or more isolated ones, might have beams of radio emission that sweep past Earth while their other radiation is too weak or pointed elsewhere. This would be a cosmic lighthouse whose brilliant rotating radio beam is the only sign we ever see of its existence. The most thrilling theory, however, is that this source represents a previously unknown type of transient event. Perhaps it is the aftermath of a stellar merger or a tidal disruption event too faint in other bands to notice, but which created a temporary, powerful radio echo. Or it could be something entirely new, a phase of a celestial object's life that our textbooks have not yet described, one where its primary energy output is channeled almost exclusively into long-wavelength radio waves. The mystery of dark radio sources forces astronomers to confront the limits of their multi-wavelength approach. We often assume that a powerful object will leave fingerprints across the electromagnetic spectrum. Finding one that does not is a humbling reminder that the universe still holds phenomena that defy our standard search patterns. This single, persistent radio whisper in Triangulum is a siren call to look harder, to develop new instruments, and to remain open to the possibility that some of the most powerful engines in the cosmos are masters of disguise, visible only in the silent language of radio static. Far from that silent radio whisper, a new galaxy might be struggling to be born in the chaos of an ancient collision. On the very outskirts of Triangulum, astronomers have pinpointed a dense, luminous clump of stars and gas that does not quite belong. This is our 20th strange object, a suspected tidal dwarf galaxy. It is not a captured satellite, but something potentially more fascinating, a new island universe being forged from the wreckage of a past encounter. The evidence begins with its location and motion. This clump sits in the galactic halo, far from the orderly spiral disk, yet it shows signs of rotating independently. The stars within it share a common motion that is distinct from the general flow of Triangulum's outer halo stars, hinting at a self-contained gravitational system, a potential galaxy in its own right. Its stellar population adds another clue. Unlike the ancient metal-poor stars that dominate Triangulum's halo, this clump contains a surprising number of younger, bluer stars. This suggests active, recent star formation, the kind that requires a rich reservoir of cool, dense gas. That is the key piece of the puzzle. During a close gravitational encounter, like the one that likely warped Triangulum's spiral arm, immense tidal forces can stretch out vast streams of gas and stars from the main galactic disk. Within these streams, the densest knots of gas can become gravitationally unstable, collapsing upon themselves to ignite new stars and potentially form a self-bound object, a tidal dwarf galaxy. Think of it as cosmic spray from a crashing wave coalescing into a new, smaller droplet. This object is not a primordial building block of the universe, but a second-generation structure, born from the debris of a larger catastrophe. If confirmed, this tidal dwarf candidate tells a profound story about the creative power of destruction. Galactic collisions are not merely destructive events that tear things apart. They are also generative factories that can assemble entirely new galactic entities from the scattered pieces. The young stars within this clump are literally made from material ripped out of Triangulum's own spiral arms during a violent gravitational pass, perhaps billions of years ago. By studying its rotation, mass, and chemistry, astronomers can work backwards to understand the severity and timing of that ancient encounter, and even estimate how much material was stripped away. This suspected dwarf is a living testament to the fact that galaxies are not isolated islands, but dynamic systems that constantly exchange and recycle their very substance, sometimes giving birth to entirely new worlds in the process. The silent construction of a new galaxy from tidal debris is a story written in gravity and motion, but the biography of a single star can be etched into the very atoms of its atmosphere. Our 21st strange object is a carbon star in Triangulum with a highly unusual isotope ratio. This is not just a cool, red giant star rich in carbon. It is a cosmic chemist whose outer layers hold a specific telltale signature. Within its sooty atmosphere, astronomers have detected an overabundance of certain carbon isotopes, particularly carbon-13 compared to the more common carbon-12. This tiny difference in atomic weight is a profound clue, a direct fingerprint of the nuclear fusion processes that once raged in the star's hidden core. For most of its life, a star like this fused hydrogen into helium in its core. As it aged and expanded into a giant, it began to fuse helium into carbon. The precise conditions of that helium burning, the temperature and density, determine the ratio of carbon-12 to carbon-13 that gets produced. An unusual ratio acts like a forensic report revealing the star's mass, its age, and the specific path it took through its late evolutionary stages. A higher than expected amount of carbon-13 might point to a particular type of mixing event, where material from deeper, hotter layers where extra neutrons were available got dredged up to the surface. But there is an even more intriguing possibility hinted at by this isotopic signature, the ghost of a companion star. If this carbon star was once part of a binary system, it could have gained material from its partner. That transferred material would have carried its own isotopic history, polluting the atmosphere of the star we see today and creating this anomalous blend. It is as if we are analyzing the chemical makeup of a person's blood and finding traces of a completely different diet, evidence of a shared meal from long ago. By reading these subtle atomic ratios, astronomers can reconstruct a detailed stellar biography. They can estimate the star's initial mass, understand how deeply it mixed its internal layers, and even deduce whether it lived a solitary life or had a dramatic partnership that altered its very composition. This one cool, red point of light in Triangulum is therefore a complex historical document. Its faint, carbon-rich light carries encoded within it the entire story of its nuclear fires, its internal convulsions, and its potential cosmic relationships, all decipherable from the precise weight of the atoms floating in its outer atmosphere. The precise atomic biography of a carbon star is written in its atmosphere, but another stellar partnership in Triangulum marks time with a slow, relentless pulse of X-rays. Our 22nd strange object is an X-ray binary system with an unusually long orbital period. In this cosmic dance, a compact object, either a neutron star or a stellar mass black hole, orbits a normal companion star. Its immense gravity strips gas from the outer layers of that donor star, funneling the stolen material into a searing hot accretion disk that glows fiercely with X-rays. Most of these systems whip around each other in a matter of hours, completing an orbit in the time it takes for a single Earth day to pass. The system in Triangulum, however, moves to a different, far slower rhythm. Its orbital period stretches for days or even weeks. This is not a minor difference, it is a fundamental clue about the system's history, its present state, and its ultimate fate. A period this long tells us the two stars are widely separated. They orbit each other at a vast distance, perhaps tens of millions of miles apart. This spacious arrangement changes everything about the dynamics of the system. The donor star is likely a giant or supergiant, a swollen, evolved star with a huge but tenuous outer envelope. Even from far away, the compact object's gravity can still pull a slow, steady stream of gas from this bloated atmosphere. This creates a more stable, less violent transfer of mass than in the frantic, close-in binaries. Imagine two dancers, one small and dense, the other enormous and billowing, slowly circling each other across a wide stage. The larger dancer constantly sheds wisps of its costume, which spiral inward toward the intense gravity of the smaller partner. The long period also implies an advanced age. This binary system has already lived through a dramatic past. The progenitor of the compact object was once a massive star that lived fast, exploded as a supernova, and left behind this dense remnant. The fact that the companion star survived that cataclysm and remains in a wide orbit suggests the supernova kick was relatively gentle, or perhaps the stars were already far enough apart to withstand the blast. Now, in this late chapter, the donor star itself is aging and expanding, finally beginning to feed its partner after billions of years of peaceful coexistence. This slow feeding process dictates the X-ray signature we see. The accretion disk may be larger, cooler, and less turbulent than in short-period systems, leading to a distinctive and steadier X-ray output. Studying this long-period binary is like finding a rare, slow-motion replay of a common cosmic process. It allows astronomers to test models of binary evolution under extreme conditions, to understand how these relationships survive stellar explosions, and to predict what happens next. In perhaps millions of years, the donor star will expand even further, possibly engulfing its compact companion and entering a new, even more volatile phase. This leisurely X-ray clock, ticking over days and weeks, measures the patient, inevitable consumption of a giant star by the ghost of its former partner. That slow, patient consumption unfolds over eons, but elsewhere in Triangulum, a brilliant, emerald spark of creation burns with frantic urgency. Embedded within one of the galaxy's spiral arms is a compact, dazzling knot that glows with an unusual and vivid green hue in specialized telescope filters. This is our 23rd strange object, a rare analog to the so-called green pea galaxies, but with a crucial twist: it is not a galaxy at all. It is a tiny, seething region of intense star formation trapped inside the much larger spiral of M33. The striking green color is a direct chemical signature emitted by doubly ionized oxygen atoms. For oxygen gas to glow this specific shade, it must be bathed in an extraordinary flood of ultraviolet radiation, the kind only produced by a staggering number of the hottest, most massive newborn stars. This region is a stellar factory operating at maximum intensity within a very small volume, a superstar cluster in the making. What makes this object a true cosmic oddity is its location. True green pea galaxies are typically small, isolated dwarf galaxies in the distant universe, entire cosmic islands undergoing a ferocious burst of star formation. Finding a region with all the same extreme characteristics inside a mature, well-ordered spiral like Triangulum is exceptionally rare. It is like discovering a single, wildly overgrown, fluorescent green weed thriving in the middle of a perfectly manicured lawn, a pocket of primordial frenzy within a settled galactic disk. The secret to its intensity likely lies in its chemistry. This region probably has a lower metallicity, meaning it contains fewer heavy elements fused in previous generations of stars. Gas with less metal cools less efficiently, allowing it to collapse into denser, more massive clumps that then form those scorching hot, brilliant stars in rapid succession. These stars, in turn, flood their surroundings with so much ultraviolet energy that they rip electrons from oxygen atoms, causing the characteristic green glow that marks this as a region of almost pure, unbridled stellar birth. This compact green beacon is a window into a different mode of cosmic construction. While the giant nebula NGC 604 is a vast metropolis of star formation, this green P analog is a single, blindingly bright skyscraper, a concentrated tower of pure energy. Its existence challenges our understanding of how such extreme, localized bursts can ignite within a galaxy that otherwise follows the calm rules of spiral structure. Is it the result of a particularly dense cloud collapsing in isolation, or the shock wave from a past event compressing gas to a breaking point? However it ignited, this tiny green ember within Triangulum proves that even in a familiar galactic setting, the universe can still conjure pockets of violence and beauty that defy all expectation. That vivid green ember of star formation reveals the power of visible light, but the true mass of a galaxy is measured by what we cannot see. Our 24th strange object is a candidate gravitational lens, a subtle warping of space-time that suggests a colossal concentration of mass hidden within Triangulum's disk. Astronomers have identified a distant background object, perhaps a far-off galaxy or quasar, whose light appears distorted as it passes through the Triangulum Galaxy on its way to us. This distortion takes the form of multiple, faint copies of the same object, or a stretched, elongated arc of light, a telltale signature predicted by Einstein's theory of general relativity. A gravitational lens is nature's ultimate magnifying glass, where the gravity of a massive foreground object bends the fabric of space itself, curving the path of light from anything behind it. Confirming such an effect within another galaxy, however, is an extraordinary challenge. The lensing mass must be perfectly aligned with both Earth and the distant background source, a cosmic coincidence that is rare enough. But within the crowded, complex structure of a spiral galaxy like Triangulum, the signal is incredibly difficult to isolate from the foreground glow of billions of local stars and nebulae. It is like trying to detect a flaw in a single pane of a stained glass window while the entire window is illuminated by a brilliant light behind it. The potential payoff, though, is immense. If confirmed, this lens would act as a direct probe for dark matter on an unprecedented scale. The amount of distortion in the background image is a precise scale, weighing the total mass of the foreground object causing the lensing. By subtracting the mass we can see in stars and gas, astronomers would be left with the mass of the invisible dark matter halo associated with that specific region of Triangulum. This would allow us to map the distribution of dark matter not just around the galaxy as a whole, but within its spiral arms around individual star clusters, or even associated with a single, massive but dim object. Is the lensing caused by a dense knot of dark matter, a massive but failed star, or an entire dwarf galaxy orbiting unseen within Triangulum's disk? Each possibility paints a different picture of the galaxy's hidden skeleton. This faint, distorted image, if real, is more than a curiosity, it is a key. It unlocks a method to weigh the invisible directly, to chart the dark scaffolding that holds the luminous galaxy together, and to test whether dark matter is smoothly distributed or clumped in ways our models have yet to predict. A single warped point of light could therefore illuminate the deepest shadow in modern cosmology. And so we arrive at the final entry on our list, a mystery that defines the very spirit of exploration. The 25th strange object in the Triangulum Galaxy is not an object at all, but an event, a cosmic whisper that vanished before we could truly hear it. Astronomers catalogued it simply as the Triangulum Flasher. In one observation, a point of light in the galaxy's spiral arm appeared where none had been before, shining with a sudden, unexpected brilliance. In the next, it was gone, fading back into the stellar background without a trace. This was not a variable star with a predictable rhythm, nor the steady glow of a nebula. It was a transient, a one-time event that left behind only a single, tantalizing data point in the archives. What could produce such a brief, solitary flash in the depths of a neighboring galaxy? The detectives of astronomy have a few suspects, each more dramatic than the last. The first is a rare type of supernova, perhaps a faint, fast-evolving one that peaks in brightness and fades in a matter of days rather than weeks. If we caught it just as it was declining, it might have appeared as a quick flare before vanishing from view. Another compelling possibility is a tidal disruption event, a star wandering too close to a black hole. The black hole's immense gravity would stretch and shred the star, pulling it into a swirling disk of doomed material that flares brightly as it is consumed, a feast that can shine for months but might also produce a sharp, brief spike if the star was very small or the encounter particularly swift. Then there is the cosmic trick of gravity itself, a microlensing event. Imagine an invisible object like a wandering planet or a faint star passing precisely between Earth and a distant star in Triangulum. For a short time, the foreground object's gravity would act as a lens, magnifying the background star's light and causing it to brighten dramatically before fading as the alignment passed. This would create a clean, symmetric flash with no lingering aftermath, a perfect explanation for a one-time event. Yet sometimes, even these exotic explanations fall short. The light curve, the color, or the location does not match any known template perfectly. This opens the door to the most thrilling and humbling possibility of all, that the Triangulum Flasher was something entirely new, a celestial phenomenon we have not yet named or understood. It could be the signature of a novel stellar collapse, the collision of exotic objects, or a previously unseen phase in the life of a star. Its fleeting nature is what seals its mystery. Without a second act, without follow-up observations, it remains an unanswered question written in light. The Triangulum Flasher is a powerful reminder that for all our maps and catalogues, the universe is still a place of sudden, brilliant surprises. It underscores that discovery is not always about finding answers, but about learning to recognize the questions hidden in a single, unexplained point of light that winks at us from the dark and then is gone forever. Each of these 25 oddities is a single piece of a much larger cosmic puzzle. When you step back and view them together, a profound portrait of the Triangulum Galaxy emerges, one far richer than a simple spiral of stars. It is, first and foremost, a natural laboratory for extreme stellar physics. From the Thorn-Zitkow object candidate forging rare elements in its hidden heart to the luminous blue variable tearing itself apart in violent outbursts, Triangulum showcases the full, dramatic life cycle of stars in ways our own crowded Milky Way often obscures. We see creation in the green pea analog's frantic emerald glow, death in the sculpted geometry of planetary nebulae, and the hidden engines of power in the ultraluminous X-ray source and the candidate intermediate mass black hole. This galaxy offers a cleaner, face-on view of these processes, letting us test our theories of stellar evolution in a new and revealing environment. Beyond stellar life and death, the collection tells a gripping story of violent dynamical history. The warped spiral arm, the vast and structured stellar halo, and the suspected tidal dwarf galaxy are not separate curiosities. They are different chapters of the same epic. They are the scars and offspring of a past gravitational encounter, likely with the Andromeda Galaxy. This history of interaction solves some puzzles, like why one arm blazes brighter, but it also creates new ones, challenging the notion of Triangulum as a quiet backwater. It reveals a galaxy that has been shaped, stirred, and enriched by external forces, its current beauty born from ancient chaos. Ultimately, this tour through Triangulum's strangeness serves as a powerful reminder of how much we still do not understand. The unidentified infrared source, the anomalous radio beacon, and the fleeting Triangulum flasher stand as monuments to our ignorance. They represent the limits of our current categories, the phenomena that slip between the lines of our textbooks. Each unanswered question, from the true nature of the quiet central black hole to the distribution of dark matter hinted at by a potential lens, connects directly to the biggest astronomical mysteries we face today: the nature of gravity, the life cycle of galaxies, and the composition of the universe itself. So the Triangulum Galaxy is far more than a pretty spiral in the sky. It is a dynamic archive, a cosmic construction site, and a hall of unanswered questions all wrapped into one. Its 25 strange objects are not just a list of anomalies, they are the language through which this galaxy tells its complex, ongoing story. A story that continues to challenge and redefine our place in the cosmos. The journey through Triangulum's wonders reveals a cosmos far stranger than we ever imagined from our quiet corner of space. From the silent giant at its core to the fleeting flash that vanished without a trace, each mystery peels back a layer of our cosmic neighbor's true nature. These are not isolated curiosities, but interconnected clues in a grander story of creation, destruction, and hidden forces. A galaxy we once saw as a simple pinwheel of light is, in truth, a dynamic archive written in the language of violent variables, sculpted nebulae, and invisible halos. It proves that profound secrets are not always found in the distant, ancient universe, but can be waiting just next door in the faint smudge of a familiar constellation. So the next time you find yourself under a clear, dark sky, look toward the small constellation of Triangulum. Let your gaze linger on that patch of darkness between its stars. Now you know that within that soft glow spins a world of silent black holes, runaway suns, and green embers of creation. A whole universe of questions just waiting for the next curious mind to decode them. Which of these 25 strange objects captured your imagination the most? Was it the stellar chimera, the phantom flash, or the ghostly geometric nebula? Let us know in the comments below. If unraveling cosmic mysteries like this fuels your curiosity, be sure to subscribe and join us as we explore more wonders hidden in the deep sky. Until then, keep looking up.